circuit pitfalls. In this chapter, we will talk about something that you have to care about when you design circuit. So sometimes when you design a circuit, you will happen to make mistakes. There are so many common mistakes, so we will see that how we avoid such mistakes. And also we will analyze the circuit and how we diagnose the cause and recommend the solution. And we'll also talk about the noise budgets and reliabilities. This is a common 2-to-1 multiplexer you may think of. So you may use only MOS pass transistor for 2-to-1 multiplexer. But you know that this is just single MOS transistor is not good at passing VDD, especially if you are having the very high VT device there. The high VT happen for NMOS is that SF corner, right? Slow NMOS and fast PMOS corner, it will fail because of the VTH is so large. You know that the internal node X never rise above VDD minus VT. So VT is also raised by the body effect. The source node is higher, so the VT is even higher. So this threshold voltage drop is most serious in this kind of a circuit. So as VT becomes larger fraction of the VDD. The simple solution is use transmission gate instead of just pass transistor. Use MOS and PMOS in parallel like this, right? So that we can safely deliver VDD and 0 voltage through the transmission gate. This is another example of a latch design. You may use the dynamic circuit technique so that the internal load X parasitic you want to store at that value onto the parasitic capacitance on the node X. So, but you may have a problem by having this kind of symptom. You want to load A onto Q so that the X is VDD. So you set phi 0, so this transmission gate is off, but then the switches of the value stored on the parasitic capacitance, the VDD, is supposed to be held high, but because of the leakage it may go down to 0 voltage, right? So the output will flip to go to VDD. So right, sometimes it flip to VDD. Why this happen? Because of the leakage, the X is a dynamic node, the holding the value. So since the charge on that node actually holding up the voltage VDD, but any leakage, sub-threshold leakage through this transistor, so we have a VDS leakage there that will disturb the voltage on the X, right? This was the VDD, and sometimes the D changed to high, and the output node here, first invert output node drive the 0. So we have a drain and source has the large voltage drop, even though the the transmission gate is off, so there's leakage, so it will discharge the value slowly, so eventually it will flip the value on the X. How we solve this issue? So we make it stabilize the X by making stable circuit, static circuit or static node by having feedback like this. So whenever the transmission gate is off, the X node is held by this feedback inverter there. This is one solution, but another solution is making the periodically refresh the node X. How we refresh the node? By having faster clock, right? Making this transmission gate is on much faster rate. So use the fast clock so that we can refresh the node X. But this may not be ultimate solution with a very large leakage, or there's a kind of ambiguity. How fast is the fast, right? So even though that is make the clock faster, sometimes when you want to test the circuit, you want to minimize the test cost. That means you want to test your circuit in slow frequency, in slow clock. In that case, your circuit want to work properly. So in that way, the number one rule is that you want to make it a stable circuit. So always try to make it the static circuit rather than the dynamic. Special case that you really want the fast logic and you have to make it to work for some satisfying your final goal, then you can try for the dynamic logic by knowing the limitation. So in that case, the test itself should be done in a very fast clock. So all the design issue and problem you have to know beforehand, right? Another bad circuit example can happen in domino AND gate, for example, domino circuits. In this domino, you may have the symptom of the following. You pre-charge the gate X, then Y becomes 0, VDD. Then you evaluate eventually Y sometime go to high, even though this value at 0 to 1, the value at the input is kind of the condition that they disable the pull down. So there's no pull down, complete pull down path enabled, but the output flip to 1. Why this happen? Because again, because of leakage, the dynamic circuit is very weak at the leakage. So X is dynamic node also, so subthreshold leakage will eventually discharge the charge. Even though the transistor, the pull down path is off, there's always subthreshold conduction there. The solution is making a very small keeper there, with the minimum size of the keeper PMOS holding up the node X. So node X is VDD, then Y is 0, and 0 output will make the keeper PMOS on, so holding up the X again. So as long as the holding up keeper device is stronger than the leakage, then you will get your circuit more robust to the leakage current. Another example is pseudo NMOS OR. So typically when the only one of those inputs is high, then y must be driven when only one of the x is driven to low and y goes to high, right? But this sometimes if in some corners it may behave differently. Even though the one of the input is pulled down, the x is not go down all the way to ground, especially when the PMOS device strength is greater than you expected. So in that case, the output just stays 0 without making a transition to high. This happens in slow, NMOS slow and PMOS fast corner. So this kind of a pseudo NMOS is very easy to fail, especially the operating principle by itself is fighting between NMOS and PMOS. So if the PMOS is too strong, then the NMOS pull down cannot pull X low enough. So how we avoid this? Just we have to check the ratio between PMOS and NMOS in all corners. So you have to be very careful about designing this kind of a circuit into the NMOS. So either you check all the corners or you just make it in static CMOS. So static CMOS is number one, first option. If you cannot meet the design requirement, then you may consider pseudo NMOS, but you have to check all the corners and also all the supply condition. The supply may vary by 10%, right? So the design check is more tough and then you can think of, so it is very challenging to verify such kind of a circuit. Another bad circuit example is just this kind of a latch. So you use the latch, the transmission gate, and weak inverter. So after you design, you get the chip back and you test it, but somehow the output is just stuck at VDD. It doesn't change at all. Why this happen? This is the problem with this is the transmission gate at the input. So the inverter may drive long line and then get to the latch, even though the driver NMOS strength is high enough, but the wire is too long and the wire resistance is too high. In that case, we may not be able to pull down the node X. So this is a brief example diagram block circuit, equivalent circuit. There we have a very long series resistance after this driving inverter. So wire resistance is too high, so you may compare to the weak inverter there, so this pull down must be greater than the pulling down, maybe, for example, must be greater than weak inverter strength. But the feedback inverter, even though you put the weak feedback inverter there, you may not expect such large wire resistance there. So solution for that. So just avoid that unbuffered diffusion input like this kind of a circuit where driver is unknown, right? So this may happen when you use the path transistor logic with the multiplexer there again. In this circuit also very sensitive to the wire resistance maybe, and the speed is limited by wire resistance, right? And also if you have a feedback small V inverter there, it may even have a high chance of failure. So having path transistor at the input for as a single block is very dangerous. So if you look at the digital library cells provided by the foundry and synthesis design flow, they never have this kind of transmission gate at the input. They always receive the signal through the gate in that region. So this kind of design is very sensitive to wire resistance. The speed is not well defined there, so you have to make sure that interface doesn't cause any problem. Another bad circuit example shown in here is coming from domino AND gate as well. So symptom is we precharge the gate while A and B's are all 0, so G is all driven output is 0. In that case, we set the feed to high. We go into evaluation phase, and then A rise, but B stays low, so A goes to rise. But G is supposed to be stay 0, but somehow G is making a transition. Why? We learned that there's a parasitic capacitance between the transistor pull down path. So the charge sharing may pulling down the Y node. That will make a wrong transition. So this kind of a charge sharing parasitic capacitance between A and B and the gate make a problem. So how we avoid this? So we just remove the charge sharing by having very small parasitic CX compared to CY. So safely the CY must be much larger than CX. Another way is just pre-charge that X node to VDD, so another device there driven by phi. Well, while we are pre-charging the Y, we also pre-charge X to VDD as well, right? Another bad circuit example, dynamic circuit shown here, dynamic gate logic. The symptom is we pre-charge the gate while transmission gate latch is hold mode, right? Then evaluate, the latch become transparent, this becomes somehow on, then X may fail. So having dynamic logic and path transmission gate like this, having very high potential of failure. This happens because between X and Y, X is a floating node, so another floating node Y may have a charge sharing. So if the Y node is driven to low and X is pre-charged to high, for example, high VDD, then this is low. When this transmission gate is on, there's a charge sharing between X and Y. The voltage will drop, right? So solution is we can add buffer after dynamic load before drive the transmission gate. So we may add the inverter there just after dynamic loading to isolate between the transmission gate nodes and the internal pre-charging node X. Another example of bad circuit is shown in here, the latch again. The symptom is the output Q changes while latch is in hold mode. In hold mode, the input transmission gate is off, but somehow the value changes, because especially when the D is driven from a long way, and so far away driver, so the VDD here and VDD from the far away or ground is different, then it becomes problematic. So diffusion we have at the input. So if the D value goes lower than minus VTH, then the transmission gate it may turn on because this becomes, let's say this is minus VTH, then we have a VGS close to VTH here. So somehow the input D is driven by the faraway driver, then the supply of the such driver or noise coupling may cause some voltage fluctuation or voltage drop on the input, right? So that may cause this transmission gate is on. So how we solve this? So we add buffer internally there, so that the slight variation on the, even though the D goes below VTH, the abnormal behavior doesn't happen, because of the input directly goes to gate capacitance, gate of the NMOS and PMOS. So this past transmission gate input has been very sensitive to some dangerous situations, such as the input noise coupling, something like that. Another bad circuit is a circuit for any circuit can be behaving differently than the expected. So what would be the principle for avoiding such kind of a bad circuit? We trying to simulate different power supply level and some abnormal environment. We model that into our simulation corners, such as some temperature variation and supply variation. So that can be another way of double checking your design. You vary this temperature, you vary the supply voltage, so that you can see that how large design margin is there for your design. Right? You can double check. So far, the circuit can behave differently when we consider the noise. What kind of the noise we can expect from the circuit? So first, the power supply and ground bounds. So whenever we have a switching happen, so there's a load capacitance, we when the input changes VDD to 0, the PMOS on, pull up current I up will flow like momentarily, like this. This is I up. If there is any resistance on the supply, also resistance on the ground line, if there's any current, non-zero current, voltage drop will be there on the supply and ground. That will actually changes the supply you in your sub block. There's also the capacitive coupling issue and charge sharing issue in domino we already looked at, and also leakage current, and also noise feed-through. Any feed-through from the coupling, capacitive coupling, might cause the design failure. So this kind of issue may result in the increased delay, more delay on your design, or incorrect computations. So we have to take that into account, and when you design the digital circuit, we have to have a margin for such kind of a situation. So how we model such margin? So we may increase the clock frequency, or we may reduce the supply voltage, we may increase the temperature, or so we can have a variety of the different range of the variable like supply, temperature, right? So and clock frequency, some kind of variation you can apply to your design and see whether your design is robust to such a variation or not. So when you make your circuit and you get the chip back and keep running it, so there's a kind of a failure. You may see failure. Initially you may see some failure, or while you are making your circuit or design working for a long time, and sometime at 2 years later your circuit may malfunction, may not function properly. So there are 3 different regions of the failure. The first, infant mortality, is first time you get the chip, it may quickly degrade. The failure it becomes high, so we may screen out during the test processing. While we are testing your chips, we can sort out the failure chips. Once the chip is on the market and you buy the chip, you actually use that chip in your application. You will see your circuit chips working properly for useful operating lifetime. Most of the time, if you buy electronics from the store, they guarantee like 2 years of operation, something like that. If the operation goes beyond 2 years, they don't get warranty your design, their product, right? So it becomes kind of some kind of the weird out. So you will see some error and failure. You need to throw that away, or you go for the service center to fix that up. In terms of reliability, we want to guarantee your product running properly for the guaranteed operating lifetime, like this. The error can be soft error and hard error. Hard error is like once the error happens, it cannot be recovered. But software error, so error might be momentarily. If you turn on and turn off, if you power off and reset it again, then your circuit might work again, right? Another thing that you have to consider is electron migration. So electron migration is kind of caused by the electron wind. So this is the movement of the metal atom along the wire. So excessive current or too much stress on a very thin line, they may cause the line or the metal line may be weared out, so it will be broken. It all depends on the current density through the area. If the current density is too high, then the metal line might be broken. So there's a certain range of the limit for DC current that is defined by the 1 to 2 milliamp per micrometer square. So this is kind of a limit. So what you can just remember is typically 1 milliamp per micrometer is the maximum kind of a limit. Rule of thumb you can remember. So any metal line, the width is like a 1 micron. The maximum current you can expect is roughly 1 milliamp. Imax is 1 milliamp. So actual number is different over the different the technology or process. So you have to refer to the foundry design kit manual. The self-heating is the another mechanism that limit the maximum amount of current. In this time, the AC current. So the current through the wire resistance generate the heat typically. So oxide around the wire is a thermal insulator. So heat tends to build up in wires. Harder wire are more resistive and slower. So hot temperature causes the wire resistance larger and making it slower. But there is some self-heating AC current limitation that is typically 15 milliamp per micrometer square. So in DC maximum, for the electron migration case, the maximum was typically 1 milliamp per micrometer wide width. But for the self-heating case, AC current, DC for electron migration, you can remember they're approximately 10 times larger, let's say 10 milliamp per micrometer for AC current is the maximum current that you can flow in terms of the AC limitations. So AC current and DC current maximum limitations are different, so you can double check the metal wire width when you design. So you have to watch out for how much current, how much DC current and how much AC current will flow in your design. So you have to double check. Okay. Hot carriers. So E field, electric field across the channel give us the high energies to some carriers. So those hot carriers may be blasted into the gate oxide where they become trapped. So we have a M- and M+. We have a channel inversion here. The electron on the surface, the electron will move from source to a drain, but because of the high electrical field, this electron will be trapped on the oxide there. This kind of a charge accumulation inside the oxide may cause the shift in VT over time. So VT shifts too far, then your circuit may fail, right? So we need to choose the appropriate VDD to achieve reasonable product lifetime. So the worst problem when the substrate current is large, so we have to try to minimize the substrate current. The highest current maybe in the device is coming from the saturated MOS transistors. So the maximum voltage for the device may apply for the inverter design. For example, we can apply VDD, maximum VDD on the NMOS and maximum VDD on the PMOS. So that will cause the maximum amount of current may flow, right? And then the very high electric field across channel will happen. So this kind of the hot carrier may happen for fast input changes and long propagation delay, meaning the input make a transition very sharp, but the output moves slowly because of the long propagation delay, with a large parasitic there. Then the current, the time for the device staying in the saturation will be longer, so that becomes more vulnerable to hot carrier effect, right? So we have to try to avoid such cases. Latch up is something that the critical, it was a major problem for the old days, like 1970s, the CMOS process before it was well understood. So if you look at the typical inverter, the layout, this is the side view, it's the NMOS and PMOS. If you look at here, there's a parasitic diode here. So P substrate here, and this N, P substrate P, and this NLN. There's a diode, BJT. This is the BJT here. And also here we have a PN, right? Another parasitic BJT transistor is there. The problem is, if you don't minimize the resistance on the body here, there's a resistance here, and for the NMOS and the substrate here, if there's a large resistance, meaning if you don't put the substrate contact near to the PMOS and near to the NMOS, then there will be large for the PMOS well resistance. For the NMOS we have a larger substrate resistance there. Then there's a small amount of current flow. There will be voltage drop between base and emitter, that will cause a large amount of current flow here. And also for the PMOS, if there's a small amount of voltage drop here, that will cause large amount of current there. So it is very critical to have plenty of substrate and well taps nearby the PMOS and an NMOS. Right? Its equivalent circuit is shown in here. So this is kind of a latch-up condition. If there's any small amount of current flow here and small amount of current flow here, the voltage in here developed, right? and then amplify the current there. That will your circuit will be totally dead. This should be avoided. So make sure you have plenty of substrate and well tapped nearby your NMOS and PMOS. So to minimize the risk of the latch up, when you design your circuit, you put the ring type of the substrate contact like this. Right? For N-well, so your N-well tap nearby surrounding your device. For the P-well tab also you can do that. So you can surround your sensitive region with a guard ring. It can be P-well here. Here it can be here N-well guard ring, or P-well guard ring, P-sub guard ring, or P-sub P-well or P-sub guard ring can be drawn to safely guard the circuit. So over voltage can damage your transistors. So do not supply the voltage more than the foundry actually device manufacturer suggested. High voltage may cause electrostatic discharge and oxide arcing and punch through and time dependent dielectric breakdown. All these kind of issues become problematic, so you cannot recover from those failures. So always use low voltage, low supply voltage for thin oxide and short channel devices. And also we can use ESD, electrostatic diode protection structure, when chip meet the real world, right? Whenever there's a pad there, inverter, the maximum voltage on the gate must be limited to VDD and ground. So we may have a reverse bias diode like this kind of structure. We call it ESD. So it is always turned off when input is between the VDD and ground. If the input is in this range, then the diode is off. If this input goes above or below, above VDD or below ground, this diode will be on, so we can limit the input voltage to VDD. So in that way we can safely protect the device. In summary, the static CMOS gates are very robust and will settle to correct value if you wait long enough. The outer circuit suffer from variety of the pitfalls. So static CMOS gate is the golden standard. If you cannot meet the requirement, you may think of a different way of implementing, like a dynamic circuit or domino. There's always a trade-off between performance and robustness. You have to double check and see all the different corners cases to see whether your circuit properly works. It is very important to check circuit for possible failure. For large chip, you need an automatic checker or script that check your design. Design rules are not worth the paper they are printed on, so unless you back them up with a tool. So you with a tool you already verify it. So don't too much rely on the design rule. You have to if the tool, simulation result or simulation tool doesn't show that that is okay, then you never use it. So you rely on the tool. You may misunderstand the paper design rule. So that should be always double checked with the tool simulation result. Okay.